So yeah, I'll be talking about a recent work on crossing number, and yeah, it's joint work with my advisor Julia Chujue and Zihan Mahabadi. So yeah, so what is a graph crossing number? The problem is very easy to state. So you are given a graph with a set of vertices and set of edges connecting them, and you want to draw the graph into the plane with fewest crossings. Okay, so what is a drawing of the graph? It is basically a mapping that maps vertices of the graph into points in the plane and maps edges of the graph into curves that connecting the corresponding endpoints. Okay, so for example, if your graph is K4, you click on 4 vertices, then this is a drawing of K4 in the plane. Okay, and this drawing has one crossing, which is this intersection between two curves. Okay, so two things are not allowed in this drawing. For example, if we do not allow one edge's image to pass through another vertex, okay, so this is not allowed. Basically, the drawing is in order to make the graph clear to you, and it has to be sort of not causing some ambiguous definition, the meanings. Okay, so this is not allowed, and we also do not allow 3 edges to cross at the same point. Okay, so basically, any clever way you're thinking about, like stick by some crossing, is not allowed. And in fact, we do know that K4 is a planar graph, so we can draw it differently like this. And this is a planar drawing, which is also a drawing with no crossings. Okay, so the problem of the graph crossing number is basically compute this drawing of the input graph, and also compute the drawing, compute this number of the input graph, and also compute the drawing that achieves this number approximately. Okay, so this is the definition of graph crossing number. It has a very long history. It was first introduced by Paul Turing in World War II. I think it's by studying some railway construction. And the crossing in a railway construction is quite dangerous for transportation, so they want to minimize the number of them. And has various applications and connections to other areas of theoretical computer science and also computer science in general. For example, graph algorithms, graph visualization, VLSI design, incidence geometry, etc. And according to a bibliography by Virtual, by 2014, there are already 700 papers written on this topic. And despite all this effort, it's still poorly understood from many aspects, and also from the aspect that we are taking today, the approximation aspect. Okay, so one thing I liked about this problem is that classical type of algorithms that we want to design for problems like LP, SDP simply just don't work for this one, because it cannot very characterize a crossing by some linear constraint or quadratic constraint like that. So basically need to do combinatorial stuff and work from first principles. Okay, so let's look at some previous work on the approximation algorithm of this problem. For general graphs, no non-trivial approximation algorithm is known. And this is very rare for any graph problem. And the strongest hardness result is only APX hard. So there's some absolute constant slightly larger than 1, showing that we can show that it's NP hard to be better than that constant approximation. Okay, but we do have one beautiful result, and that's towards understanding this quantity crossing number, which is this crossing number inequality. Okay. This inequality says that as long as the number of edges is larger than 4 times the number of vertices, okay, so the average degree is larger than some constant, for example, 8 or 10, then the crossing number has to be on the order m cubed over n squared. Okay. This has been found independently by Atesh, Shivatong, and Simirdi, and independently by Layton. And at the very beginning, the proof is complicated, but later on, people have been finding a very simple probabilistic proof. Do you take anything away? This can be a proof that you want to look at. Okay, a simple probabilistic proof to prove this seemingly non-trivial, very non-trivial inequality. But from our perspective today, we want to get something out of this inequality. So our understanding toward this inequality is that as long as the graph is a little bit dense, the crossing number has to be very high. So on the order m cubed over n squared. Okay, a little bit dense meaning it's larger than 4 times n. Okay, and the problem is really interesting when the graph has a very good drawing, and it depends on whether or not we can find it. Okay. So therefore, it is reasonable to look at cases where the graph is not that dense. Okay. For example, if you are given a clique, then this inequality shows that no matter how you draw it, you are doing approximately optimal already, because the crossing number is at least n to the 4. And However you draw it, as long as you make sure that every pair of edge cross at most once, it is at most n to the 4 crossings. So dense graphs are not very interesting according to this inequality. Therefore, it's reasonable to look at sparse graph in which the max degree is bounded by some constant or slowly growing function of n. And this is going to be the focus of our talk. Okay, approximating crossing number and drawing unbounded degree graphs. And even in this special case, there are not very many previous results that are known. For a very long time, the strongest approximation for this crossing number is O tilde n approximation. Okay, this is even on bounded degree graphs. And actually, the result is there's an algorithm that, given bounded degree graph, finds n plus CRG crossing drawing. So if CRG is very small, then this gives the O tilde n approximation. And later on, some logarithmic factors are shaved off by subsequent works. And in a recent breakthrough, this was further improved to n to the 0.9 by a sequence of 2 papers, first by Chuzhou, Mukherjee, and Siridopoulos, second by Chuzhou. More recently, this was further improved to square root of n by a sequence of 2 other breakthrough works by Kobayashi and Siridopoulos. And this is up to like stock 19. This is square root of n is the best we get. I'm going to present 2 results, and both on this problem. The first result is a work like 3 years ago. We slightly further improved the square root of n to n to the 0.488. Okay, so this seems like a modest improvement, but more important message that we believe that our previous work shows is that it paves a way towards much better approximation. So what do I mean by that? If we look at our previous algorithm, which I'm going into like right after this introduction, we will see that all previous works use the same algorithmic framework. And this framework is shown to be just giving us square root of n approximation at best. Okay, and what we are doing in this work 3 years ago is we get around this barrier. This is the more important message to we want to show in the previous work. Use a modified framework to break this barrier, and this n to the 0.488 is really just a concept, a message of concept that this new framework can do better than old ones. Okay, the second work. Okay, so this framework, this modified framework also reduces the problem to a related problem that I'm going to show later, called crossing number with rotation system. Okay, and the second work, we follow up this reduction and look at the new problem called crossing number with rotation system, and we design the n to the little 1 approximation algorithm for the new problem, which combined with the previous reduction, give a n to the little 1 approximation for the whole crossing number problem, still unbounded degree graphs. Okay, so these are the 2 results that I'm going to present today, if time allows, and hopefully I can present completely the first one and the second one illustrating some high-level ideas. So is there any questions on the results so far? Yeah. Or yeah, so yeah, this is all about bounded degree graphs. Actually, if we look at general graphs, then the approximation ratio here, there's a poly max degree here. So poly delta, I'm ignoring that on the slide. Yeah. Okay. Yeah, any questions? Okay, so before I dive into part 1, part 2 of the paper, give you first an idea what is this new problem is. Okay, so we're going to reduce the crossing number problem to this problem and then solve this problem approximately. Okay, 2 parts. So this is very similar to the crossing number problem. Apart from the input graph, we're also given for every vertex a circular ordering on its incident edges. Okay, so for example, this is a graph and V1 is incident to 4 vertices and 4 edges, then we're given an ordering 1, 2, 3, 4 has to be this way. And we're going to find a drawing of the graph that respect all these orderings. So in the drawing we find for this graph, this 1, 2, 3, 4 edges have to enter V1 in this order clockwise. Wait, okay. Yeah, clockwise or anti-clockwise, but it have to be in this order. You're given an order, but you can decide this flip status. So this is the new problem. Okay, so in this problem, the degree is no longer bounded. Okay, so we want to start with the bounded degree graph, reduce it to an instance of this new graph with degree not necessarily bounded anymore, and solve this approximately. This is going to be part 1 and part 2 of the talk. Okay, so now let's dive into part 1. Okay, so now let's first let's look at how previous works like design algorithm for this crossing number with monodegree case. Okay, so they all use the same framework, which is the framework that we are going to get around. What is this framework? It's a very simple one. It has 3 steps. First, compute a planarizing edge set of the graph, where a planarizing edge set is a set of edges whose removal leaves the remaining graph a planar one. Okay, so I want to remove some edges so that the remaining graph is a planar graph. And the planar graph has a 0 crossing drawing. Okay, and that's what I'm going to do. I compute the drawing of the remaining graph into the planar one. Okay, I do know it's a planar graph, so I can do this. And then we add the missing edges back. So I add the deleted edges back. This completes the drawing. Okay, how did previous work use this framework? Let's look at each of the steps in detail. Okay, so a simple example of how this framework is done. If the graph is K5, we do know K5 is not a planar graph, right? But removing any edge leaves the planar subgraph. Right? So this is a drawing of K5 minus 1 edge in the planar way in the plane. And we add this missing edge back. This is how we implement this framework, just a very quick example. So how to turn it into an algorithm? Let's look at this first step first. Okay. So it's not hard to observe that there exists a planarizing edge set of size approximately CRG. CRG is the crossing number of the graph. Okay. There exists a planarizing edge set. Why is that? If we look at the optimal drawing of the graph, and for every crossing, we take out one of the edges that participate in this crossing, then we are guaranteed that the remaining graph is a planar one, because we have already dealt with all the crossings. Right? For every crossing, we take out one edge, so the crossing doesn't exist anymore. Okay, so they exist. And CRG is sort of the best quantitative bound that we can get for this planarizing edge set. Because if we just have a graph that is this is a disjoint union of K5s, okay? So crossing number is basically the number of copies, and you have to remove the same number of edges in order to get it planar, right? So this is the best quantitative bound. And in the breakthrough work, sequence of 2 works by Kobayashi and Sidopoulos, they basically get a very nice polylog approximation algorithm for computing the smallest edge planarizing set. Okay, so basically combined together, they show that we can find a planarizing edge set with size probably CRG, approximately CRG. Okay, this is what they show in this 2 work. This is basically the way we implement the first step of the framework. Okay, so how to implement the second and third is also by previous work. In the previous work by Trudeau, McCarthy, and Sidopoulos, they show that given an edge planarizing set, we can find a way to implement the second and third step in order to compute a drawing whose number of crossing is approximately E prime times CRG plus E prime. Okay, this is via a sort of drawing finding algorithm, but this we can show. So combine these 2 results together, we can show that we can compute a drawing with CRG squared crossing given any graph. Okay, so because E prime is CRG, so CRG times CRG plus CRG is CRG squared. Okay, this is how they get like CRG squared through this framework. And recall that we have a n plus CRG approximation algorithm, and combined together with this CRG squared, this gives a square root of n approximation. Because if CRG is larger than square root of n, then n plus CRG is square root of n approximation. If CRG is less than square root of n, then CRG squared itself is a square root of n approximation. So this is how to get square root of n. And however, what I mean by this framework at best give us a square root of n is the following. There exists a graph with a planarizing edge set size E such that if we just want to draw this graph in the remaining graph being planar way and adding the edges back, if we want to draw the graph in this way, then we have to incur at least K squared crossings. Okay, there is such an example, it's a very simple one. If you're interested, there's no board, okay. Yeah, we can like draw it on board sometime. And it's also in the 1-page appendix, in the appendix A of one of our papers. So this is basically showing that CRG squared by this framework is tight. And therefore, square root of n also is tight, like for now, the best we can get from this framework. So what we do in first result is we proposed a modified framework that gets around this barrier. Okay, so our framework is also very similar to the previous one. It has 4 steps instead of 3. And the first step is identical to the previous one. And we will be actually just using the previous algorithm for computing a planarizing set. And after that, we allow ourselves to augment this augmenting set into a bigger one, such that the size is still not very large, approximately CRG. Okay, and apart from that, we have some additional properties of the remaining graph. Okay, and the third and fourth step is identical to the previous second and third step. We now draw the graph in the plane and add missing edges back. It is the additional property that ensure us that there exists a near-optimal join that can be produced in this framework. Okay, so this is like a additional property that I will go into that really change the game. So the first question is, does this modification work at all? And what we show is it does in the first result. What we show is we can compute, basically augment an input planarizing set to a bigger one called E double prime, such that there exists a join approximately optimal join, well, with probability CRG crossings, which means it's approximately optimal, no longer CRG squared, okay? Which only edges of this augmented set participate in crossings. Okay, so this is also a little bit from the previous requirement in which the remaining graph is joined a planar one, but we can add edges that create crossings with the remaining graph. Right? That is basically saying every crossing involves at least one deleted edges. But here we are requiring every crossing involves only deleted edges. It cannot even cross with the remaining graph. All crossings have to be like between a pair of deleted edges. Okay, so planar graphs, the remaining part we are draw safely in like in separate disks, and they're safe in their disks. They will not be crossed anymore. This is what we can show. But the more important message is here we get CRG instead of CRG squared. This is what we mean by get around this barrier. So if we can, like for now, there exists a join. For now, in this result, we can show there exists a join. If we can show we can find such a join, then we immediately get a polylog approximation. Okay. However, we can for now only show there exists. And in the second step, we are going to approximate that. Okay. And it can be shown that basically this is a way of implementing the second step. Okay. Given an edge planning set, we compute a bigger one that satisfies these properties. And it turns out that implementing the remaining two steps is equivalent to solving an instance of the new problem called crossing number with rotation system. And that is what I mean by reduce this problem to the new problem. Okay. Okay, so let's look at how this main theorem is proved in the first part. Okay, let's look at the main theorem again. There is an algorithm that given a graph and edge planary set of size probably CRG, we can compute a bigger one, an augmented planarizing edge set with also size probably CRG, such that there exists a drawing with approximately CRG crossings in which only edges of E double prime participate in crossings. This is a theorem we want to show. Okay, let's look at some intuition. How are we going to do it? We are going to, we are given a graph, we are given a set of edges whose that is already sort of removed from the graph, and we are guaranteed that the remaining graph is planar. We want to ensure that the remaining graph has some additional properties, and by that we look at each of the connected components in the remaining graph. So the remaining graph can be already disconnected because we have removed some edges. So we look at each of the clusters, connected components. If they satisfy some property, we basically just forget about it and just leave it here. We do not modify it further. If it doesn't, we want to further decompose it to add some more edges of it into our augmented planarizing set. So it is further decomposed into smaller ones. Okay, we want to recursively decompose them by removing iteratively edges from it so that eventually all clusters satisfy some good properties. And that's the way of proving the main theorem. We just need to guarantee that these properties are achieved and we haven't removed additionally too many more edges. This is what we're going to do. So what are the good properties that we want to ensure? Here are three properties, and I'm going to show why these three properties are enough for us. These three properties are first, three vertex connectivity. It means that the graph is three vertex connected. So between every pair of vertex, there are three vertex disjoint paths connecting them. Or in other words, removing two vertices does not disconnect the graph. Okay. So, and strong planarity. I'm going to. Yeah. So what is strong planarity? A graph is planar, but also strong planarity means we have deleted some edges in the graph. And these edges may be sort of incident to some of the vertices in the remaining graph. Okay, so this is a connected component in the remaining graph. And we have deleted some blue edges. Is this blue or purple? Okay, so we have deleted some edges so that some of these edges are incident to some vertices inside this cluster. And these orange vertices this is orange, right? Okay, are called boundary vertices because they are like in view of this blue vertices, they are sort of like at the boundary of this cluster because they are what's connecting to the outside world. Have to lie on the same face of the planar drawing. Okay, so this is a planar graph, and it is 3 vertex connected planar graph, so it has a unique planar drawing. I'm not sure if you like aware of this. So this is sort of classical result in graph algorithm. It's 3 vertex connected and planar, so it has a unique planar drawing. And what we are requiring now is in this unique planar drawing, all boundary vertices lie on the same face of the drawing. In this case, it is the case, right? We do not look at the blue edges or purple edges. In this unique planar drawing, there's 3 orange vertices, both all lying on the outer face. This is what we require. Okay, so basically we know like how the remaining world is connected to it by ensuring the strong planarity. And boundary wall linkness. It's basically saying that these 3 orange vertices are sort of well connected in this cluster. I'm going to provide a rigorous definition later, but it's not important for us. So it's like very well connected inside it. We can route somehow all to all like that. Okay, the previous work by Chui shows that if we're given a graph and we remove a set of edges such that the remaining graph, each of the connected component satisfy these 3 properties, then there is a near optimal drawing in which only edges of this deleted, in which edges of this cluster don't participate in crossings. In other words, only the remaining edges participate in crossing, and there exists such a drawing, which is near optimal. Okay. This is the previous result. I'm going to show by just a collection of pictures why it is true, and then show how we use this to prove the first main theorem. Okay, why this is true? We want to start with optimal drawing and massage this optimal drawing into another one in which these green clusters do not participate in any crossing. Okay. Along the way, we do not increase the number of crossing by a lot. Okay, let's look at an example. So in this graph, blue ones are the edges that we deleted from the graph, and the green one is one cluster in the remaining graph. And the orange and the red one is what is like remaining of the world. What is the remaining world? So we will be only looking at the green part. Okay. So blue edges are deleted from it. We are going to sort of massage the optimal drawing in which green parts are disengaged from the whole drawing. And the green part is satisfying these 3 properties. It's 3 vertex connected. It is strong planarity because in this planar drawing, A and B lies on the boundary of the same face, and they are well connected, boundary well linked. Okay, so this is the green part. The first step we are doing is use this boundary wall linkness to find a set of passes routing this A and B to a unique vertex inside this cluster, which is hopefully via edge destroying pass, but it's also okay if we just route it to a single vertex via low congestion passes. Okay, so this is crucial passes that we'll be using. Then we remove the whole drawing of the green part from the picture, and just this is what it remains. Okay, we will first redraw the blue edges by starting with their original image and extend them along the path we have been finding to the image of the vertex that we have been finding. Okay, so blue vertices already they like merge at A and B. Now we let them merge at C by routing along the original image and extend them along the new path. Okay, then we place a disk around C and put the edges, put the whole drawing of the green part inside the disk. And then finally we reroute this blue curves to their destination A and B, because there is A and B in the planar drawing that is lying on the same face, and we turn that face into the outer face, and we route them through the boundary like inside the sticks to A and B. So you can basically see that after this series of operations, the whole green part is disengaged from the remaining wall. Right? It is placed in a very small disk, and they no longer participate in any crossing. This is how we sort of iteratively turn one connected component into a isolated one. It is joined in small disks. And we do this for every green cluster. Okay, find one, do this, find one another. And eventually there's only blue edges, big blue curve that we see. Everything else is very small inside small disks. Okay, so if we like look at what is happening inside this, is showing on the right. Okay, so yeah. Mm-hmm. Yeah, so So it's basically we are routing via low congestion passes. Okay, so low congestion means every edge is not used too many times. And for example, if there's one crossing in the optimal drawing, then at most A edges use this, B edges use that, and so yeah, it depends on which part of the crossing you are looking at. It is the crossings created by this blue passes, or if it is just a blue pass, it's not related to the planar drawing here. It's just that the congestion is low. So every crossing is not blown up by a lot. Yeah, this is how we bound the crossing. So this is, hopefully I have make some intuition on how this theorem is true. So why is this true, that we can iteratively massage the drawing so that we can eventually get this. And the remaining work for us is to show that we can indeed, like given a graph, an edge planarity set, augment it so that we get another one, get a bigger one that the remaining graph satisfy all this property without removing too many additional edges still inside the CRG. Okay, the algorithm is basically look at a cluster and try to remove more edges from it, further decompose it into smaller ones if one of these properties is not satisfied. Okay, and now let's look at three properties, like each of them in detail. So first, boundary wall lengthness. I'm not sure how many of you know the word expanders. Does expander sound familiar to you? Okay, so wall lengthness is basically another way of saying a graph is sort of an expander. Only an expander means the whole graph is well connected. A wall lengthness means in the graph, a set of vertices is well connected. So in other words, wall lengthness showing that the graph is expander with respect to some points. So can basically route whatever you want on a set of points. This means this set of point is well linked inside the cluster. And we do have our existing algorithm for computing a well linked decomposition, just as expander decomposition, if it rings any bells for you. Okay, so basically we find a sparse cut it. If the graph still has a sparse cut, we cut it. Furthermore, every time we cut should be a sparse cut and can be charged to sort of graph size. And eventually we can guarantee that we do not cut too many more edges in order for the each of the remaining component to be yes, standard version. Yeah, so it's sort of local version of expander. Yeah, I hope that, I think your understanding is correct, but I don't have a more clear, another way to state it. Yeah, I think that's right. So we have existing algorithm for computing such a decomposition. So this sort of can be done. The second one is sort of tricky. We want to ensure strong planarity because that it require for every kinetic graph in the remaining, for every kinetic component in the remaining graph, all boundary vertices lie on the same face. So in this graph, let's say green part is the kinetic component of the remaining graph. Blue edges, purple edges are what have been already deleted from the graph. So the orange vertices are the boundary vertices. Okay, now there are 6 of them. 3 lie on the inside face, 3 lie on the outside face, and it is not what we want. Okay, we want all of them to be on the same face. Okay, so basically in this example, what we can do is delete one edge per cycle in order for the inner face and the outer face to be merged. Okay, but it can be that just there are too many cycles and we're forced to delete too many edges. So the way to get around it is that we want a weaker one, which is the bridge property, which is no longer requiring that all the boundary vertices lie on the same face, but only requiring that all the boundary vertices that are connected in the remaining graph lie on the same face. So these 3 are connected in the remaining graph. That 3 are connected in the remaining graph, but all the 6 ones are not connected all to all in the remaining graph. So in this case, we only require that these 3 lie on the face. The other 3 lie on the same face, and can be a different one. Okay, all this is in order for us to know how the remaining world intersect with this cluster. So they do not really need to lie on the same face. As long as we know how they can connect to this cluster, it's enough. And it turns out that we can ensure this. For example, if we are still having another edge connecting x to x prime, then these 6 vertices are again connected in the remaining graph. But in this case, we can show that we can now afford to delete one edge per cycle. Because if such a structure exists, then we can show that no matter how they're drawn, they have to incur at least like number of cycle crossings. And now we can afford to do that. This is by strong planarity and three vertex connectivity. Without them, we cannot show this. Okay? This structure is already very bad, no matter how we draw it. Okay, so yeah, this is the idea of getting a second property. Eventually, we replace it with a weaker one and stick by, still survived. And obtaining like the combination of second and third is already very tricky because you want to find a sparse cut and cut it. It may destroy the bridge property. So you find another cut to ensure bridge property and it may destroy well linkness. So you can sort of doing it over and over again, back and forth. And it's not very trivial to show that we can achieve them both, but it turns out we can. Okay, hopefully this makes any sense. And for the first property, three vertex connectivity, we still do the same thing. We eventually replaced it with a weaker one, which is, we can forget about the details here, but instead of being three vertex connected, we want it to be two vertex connected. And there's the number of two separations small, and we can sort of augment it to vaguely view as it's actually a three vertex connected one. So three vertex connected graphs, if the graph is planar, it has a unique drawing. But for two vertex connected one, it doesn't have a unique drawing. But the unique drawing is up to flips according to this separators. Okay, so if you say this part and this part have two vertices in common, you can sort of flip the whole drawing of this part just along this two vertex to a small region in the other side. So all the drawing is not unique, but it's up to this kind of flips. And we are requiring that we know all kind of this combination of flips. The number of two separators small, meaning there are no too many flips. Okay, this is basically the idea. The idea is, I'm not going into the detail of that, sorry. We replace it with a weaker one and eventually get around it by still making the previous slides of pictures going through. So even with this weaker one, we can still massage the drawings in a similar way as the previous slides have been showing. Okay, so find the passes, extend, place ball disks, place the drawing inside disk, reconnect them. Even with this weaker one, we can still do it. Okay, this is the first part of the talk. And what we are left now, we have showed that given a graph and a set of edge planarizing set, we can augment this set such that there exists a near optimal drawing in which all this like remaining connected component is joined in a separate disk. Okay, recall what the picture shows. We have sort of massaged the drawing so that each green part is joined separately in the disk, which is sort of disjoint from the outside wall. Okay, and we are guaranteed that there exists a near optimal drawing in this way, okay, such that only blue edges participate in crossings. And what we're required to do, like what we are left to do, is find a way of adding these blue edges back so that the number of crossings is minimized or approximately optimal. Okay, and as these clusters are three vertex connected, it has a unique planar drawing. So in this unique planar drawing, these vertices, the ordering of these boundary vertices on the like the unique phase that they're at is also fixed. So if there are three vertices, then because this drawing is up to flip, then these three vertices, there's a circular ordering on them on the outer face. And therefore, it also induces a circular ordering on all these incident edges. Okay, so 1, 2, 3, and edges 1, 1 prime, 2, 2 prime, 3 prime, this induces an ordering on them now. And the drawing we're going to find, which is the drawing of blue edges, must respect this order. Okay, this, yeah. So the setting is we are given a graph and an edge planarity set in which we have already which may already disconnect the graph. So we have clusters. We further remove some more clusters so that the remaining graph is only green ones. What we are guaranteed is there exists a near optimal drawing in which these green ones are drawn in this way. It remains to find it, which is what we are going to do in the next part. Yeah. Yeah, so we find the two separators or one separator and decompose it so that the remaining graph can be three connected. We will continue to do so. Okay. So this can be viewed as a very pre-processing step. Okay. Because if your graph has a one separator, then you can draw two parts separately and just glue them at this point. This can be all in the pre-processing step. Okay, and one way to draw this, blue edges is we can now view each green part can be contracted in a single vertex. And now we just have edges attached to it in the circular order that we must respect. And this is one of drawing the remaining graph. And this is what we mean by reduce the problem to the problem crossing number with rotation system. Okay. Now you can see the rotation thing works. Okay. Yeah. Yeah, it is a multi-graph now. Yeah, very good point. So the degree is no longer bounded, and the number of edges can be much higher than number of vertices. Yeah. Okay, that's what we're going to do in part 2. So let's look at this problem again. The input graph is the input is a graph, and also instead of only just a graph, for every vertex a circular ordering. Okay. So actually, we can choose the flip status as we mentioned before, because the 3 vertex connected graph has a planar drawing. It has a unique planar drawing, but that uniqueness is also up to flip, okay, up to the flip of the whole graph. So the flip of the circular ordering is also up to flip. So we're given an ordering, but we can choose the flip status. It's just some small technicality of the problem definition. And we want to output a drawing that respects all the circular orderings that have the minimum number of crossings, approximation. This problem has been very slightly studied in previous work. Okay, so in previous work, if we just look at the cubic graphs where the graph has max degree bounded by 3, then this problem, the claim is it's just equivalent to the crossing number, because if we want to impose a circular ordering on 3 things and still allowing flips, it's basically imposing nothing. Okay, so there's no rotation requirement at all. Degree is just bounded by 3. And in the cubic graph case, the strongest hardness result is already APX hard. So that APX hard just implies the APX hard for this problem, because it's equivalent in the cubic graph case. And that's the strongest hardness result we get. Okay, and there is a approximation, which is n to the 4 approximation. This seems a little bit weird, but as was just mentioned, the number of edges can be much more higher than the number of vertices. So this n to the 4 is still non-trivial. Okay, in the plane case, it's n to the 4 is whatever crazy, right? So, but now it's still non-trivial. Can be just very few vertices and many edges. The thing is, you have to respect the ordering, so you need a lot of work to do. Okay. So, in our work, we are going to show a algorithm that, given such an instance, compute a solution with n to the 1 times OPT plus EG crossings. Okay, so we basically compare ourselves to OPT, which is what we should, but also the number of edges. Recall this number of edges is what is the augmented edge set. Okay, it's the blue edges or purple edges, I'm not sure. And it has size approximately CRG, which is CRG is the CR of the original graph. Okay, so we can compare with the size of that. And that is why we put a terms EG here. And this EG is sort of crucial for us. We compare ourselves to compare with, we allow ourselves to compare with not only OPT, but also EG, which is we can just allow ourselves to have more crossing if the number of edges is large. Okay, for abstractly for this problem, EG can be larger than OPT, but we do know that in our reduction, EG is just CRG. Okay, green. Okay, so yeah, I hope that I can give some ideas on how this n to the 1 is achieved. If there's still some time. Okay, so the framework of this algorithm is divide and conquer. So we want to divide input graph into smaller ones and further smaller ones and small enough ones until we can use some simple algorithm to compute a near optimal drawing on. For example, the graph has smaller enough size, like log n size, so we can sort of enumerate all kinds of possible drawings and find the best one. And for every subinstance, we want to find this subinstance give birth to compose the drawing of them back into a drawing of the instance, and top-down step and bottom-up composing steps combined together, they give a divide and conquer algorithm. In order for this framework to work out, these 3 conditions need to be satisfied. So if we just look at one step of dividing an instance G into 3 subinstances G1, G2, G3, as we are comparing ourselves to EG and OPTG, we wanted their sum EG, sum OPTG to be at most OPT of G and E of G respectively. Okay, in one step. And also there has to be a combining drawing algorithm that combines all these subinstances drawing into a drawing of the original instance G, in which the number of crossings do not blow up a lot. Okay, so for this divide and conquer framework to top down and bottom up things to work, this have to be satisfied. Okay, and want to show you in like a few minutes why this can be done like separately. First, let's look at how we create the instances. It's basically take one big one, take a big graph and decompose into smaller ones. So the simplest approach of decomposing an instance is basically find a cut, remove all edges in this cut, and be done with it. This G1, G2 is what we are left. Okay, we just want to find drawing of G1, drawing of G2, and hopefully you can combine them. It's easy to see that OPT, the sum of OPT is less than OPT of G, because the optimal drawing of G already gave induced a drawing of G1 and another drawing of G2, and all their crossings is the crossing in the optimal drawing. So OPT is good, EG is good, EG is even smaller, the sum of them. Okay, but combining these two drawings turned out to be a problem. For example, if this is a drawing of G1, this is a drawing of G2, we want to combine them into a drawing of G. We had to add the missing edges back. Okay, and since we have no control of how these two drawings look like, in the worst case, it's possible that adding one edges back will create crossings with many others. Okay, every single one deleted edges, we add them back and create more crossings. And we may end up paying number of deleted edges times EG, and this is too much. We cannot afford. So we want to make a slightly like modified version of constructing subinstances. Instead of just taking G1 and G2, we place a new special vertex, which denoted by red circle, and connect it to all the cut like endpoints of the cut edges of G1. Okay, and for G2 we do the same. Now these are the two subinstances we're getting. We're recursing on them instead of just G1 and G2. This is new G1, new G2. Now I'm claiming that this modification resolves the composing the drawing hazard. And why is that? If this is a drawing of new G1, this is a drawing of new G2, what we're going to do is start with drawing of G1. Again, place a disk around the image of the special vertex, okay? And place the whole G2 inside this disk. Okay, here a little bit careful because we want to first carve out the small disk around the special vertex. Now all the purple curves touch the boundary of the green one, and we view what is inside this green one as the outer face. So if we turn them into like a picture of this, this is like all the purple curves touch the green boundary in this way. And we place the whole thing inside the bigger disk that we have just painted. And we reconnect this purple curve within this annulus region in this way. So this is a way of getting the whole graph drawing. Okay, basically, originally the cut edges are now like two sets of edges, and we connect them correspondingly. We can still see that there can be crossings happening in this annulus, right? So one technical part of the paper is recall that we still have the freedom of defining the rotation system here and defining the rotation system there. Okay, we are recursing on a crossing number with rotation system instance. So every vertex comes with a rotation, and we have the freedom of defining what is the instance we want to recurse on. And we can delicately design the rotation systems of these two vertices in order to make sure that either just within this annulus, no crossing will happen when we want to combine them, or the number of crossings can be charged to OPT. It's one technical part I'm not going to, but this is basically saying the composing can be done at a small cost. Okay. So actually, we will be not cutting the graph into two, but we will be simultaneously cutting the graph into many parts. And for every part, we create a class-based new instance by basically, for every edge that is coming out of it, contract the remaining wall into a single vertex. Okay, this is a cluster-based instance. So for two, we can just combine them in the previous slide. Okay, small disk, annulus connecting this way. But for many of them, we want another central-based instance to connect all of them together. This is just technicality. What we are doing is not decomposed by two, but three. And for that, we need some more instance, which is the small complication. And this whole thing is called basic disengagement. Not sure we want to go back to it again. Okay, just a very last small part. In this way, we basically have dealt with the composing algorithm. Basically, we can like select a way of constructing subinstances and have a way of combining them without paying too much of a cost. There's still two things to satisfy, OPT and EG. Okay. Now, originally, if we just look at the old G1, old G2, OPT, is natural, right? Because optimal solution give a G1 drawing and G2 drawing. But now we add new vertices and new edges to it. OPT is no longer guaranteed. We want to satisfy this. Like decomposing it into two, you see, it's probably not a big deal. But in fact, we're decomposing it into many, so it can be hazard. And saying if there exists a set of passes connecting the cut edges to one vertex on the right, so that the passes are edge disjoint, then we can obtain a drawing of G1 out from the original drawing just by looking at the left part of G and the image of all these like entire passes connecting it to the vertex on the right. Basically, viewing each entire orange one plus green one as the image of this purple one. Okay. In this way, we extract from the original optimal drawing a drawing of G1, new G1. Okay. And this edge disjoint ensures that this like images of the new purple curves no longer like, cross a lot. Actually, we do not need them to be edge disjoint. Again, we just need low congestion. Low congestion implies we do not blow up every crossing by a lot. So this is a property that we want for the clusters. So basically, we want paths in the order graph to use them to help us drawing the new edges, and low congestion routing means cheap drawing of G1 and G2. So we want a property of the remaining the cluster, which is the boundary edges can be routed to a single vertex, which is routing to a center property. Okay, I think I'm going to skip something, but routing to a center, in a sense, implies route to all. So if you can route to a center, then you can distribute the flow back to all. So routing to a center is stronger than all. But route all is something we're familiar. It's just the well linkness or expander like that. Routing to a center is not what we're familiar with. And one technical thing is here, we show that well linkness is enough. Okay, route all is well linkness, but well linkness does not like give back a routing to a center thing. And what we are showing in this paper, in another technical part, is well linkness is enough, but only in our purpose. So for a well linkness cluster, either we can find a random routing to a center, or some other thing happens. This some other thing is kind of bothering, but it's a good thing in our crossing number computation. It's basically saying the trouble created of this cluster, it can be charged to the cluster itself. The trouble is the boundary edges. In the worst case, every pair of them may cross once, and this creates delta C squared, number of edges square crossings, and it can be charged to OPTC plus EGC. So the cluster can handle its own trouble. This is sort of important. Without this or condition, the whole thing is not true. So officially, well linked cluster does not imply routing to a center. But with this thing, we can show that. It's a very technical part. Some comments is if we want this congestion, if we want to remove this expectation, then it's not going to happen. And if we just want to ensure expected congestion, not squared, it's easy because well, basically well linkness can just give you sort of polylog congestion flow. You're still familiar with something about expanders. Okay, so this congestion square is what is sort of technically hardest in this part. So where do we need congestion square back? If A passes take this edge, B passes take this edge, eventually this crossing may give birth to A times B crossings, and only A squared plus B squared can be bounding A times B. Okay, so expectation of A cannot be bound, only A squared plus B squared. So this is why I need it. This is sort of very technical. It's already taking 1/3 of paper length already. And routing to a center, what we have been shown is we have well linkness, and that is enough for us. However, we want to like decompose the part into two. So we want these edges to be routable in G1 and also routable in G2. So it is sort of boundary edges is routing to a center inside it and also routing to a center outside it. It is called doubly well linked. We still need stronger one. And another technical part is showing that, okay, still well linkness is enough, but it comes as a cost. The cost is now the basic disengagement needs to be much more complicated. Specifically, the basic disengagement for every cluster, it can be viewed as contracting the outside wall into a one vertex. But now we may have to decompose a further like outside wall into different parts. And this is the instance that we run now, we recurse on. Okay, So the main thing, mainly technical takeaway here is just well linkness is not. It is far from obvious that it is not, but through two very technical results, we can show it is not. It comes as a cost, which is the basic disengagement need to be turned into advanced ones, which is much more complicated. And it is enough, like by that I mean routing to a center can be achieved. And the random routing to a center, both inside and outside, can be achieved, all just by well linkness. So we have basically like guaranteed these two properties. The remaining one, not going into the detail, is basically find the balanced, mean balanced cut recursively until the size is smaller. Okay, we want the number of edges to be bounded, but in order for the recursion depth to be not very high, we also need the number of edges to be like decreased by a significant factor, which is also into a little one, and this into a little one need to be larger than the previous loss we incur. And this we just apply approximate mean balance cut. Mean balance cut meaning a cut in which the remaining, each of the remaining component has less than 90% of the edges or vertices or whatever. Okay, when we just compute the mean cut over all this balanced cut. Okay, there's a previous work showing that if the mean balance cut is large, then OPT plus delta times EG is large. OPT is the crossing number, okay, crossing number, and delta is the max degree times EG is large. So this is a corollary by planar separator theorem. I'm not sure if you know it. The planar separator theorem, in a planar graph, you have a separator of square root of n sides. And making the crossing really just artificially planarize a crossing by placing a vertex at this crossing. We do it for all vertices, we get a planar graph. And sort of this square root of n is what it comes from, the planar separator theorem. Okay, the whole thing square root of n. We're only not dealing with general graphs, but planar graphs. So this shows that as long as the degree is not crazy, crazy means one vertex almost take all edges, either the OPT is large, in which case we do not worry about this graph at all, because like the cross number is already too large, so drawing it arbitrarily is almost optimally. Or the mean balance cut is small, and then we can afford to cut it without cutting too many edges, and we recurse. Okay, so it turns out it's an NP-hard problem, so we can only approximate balance cut, and on and on it goes. So basically, a whole algorithm for the second part is we first apply mean balance cut recursively until the size is small enough by n to the purple little one factor, means something large, and then we apply well-linked decomposition to get well-linked clusters. That's basically it. The hard part is to show why this is true by two technical big parts. Okay. However, this only deals with a case in which there's no crazy degree vertex. Okay. I'm not sure if you're still like following it. Maybe I'm just putting too many details here. Sorry for that. But the message I want to say is, in another case, the algorithm is also appears very different. It's used as completely different of the framework disengagement system. We will encounter other type of clusters, not necessarily small ones, but slower ones, and will be repeatedly again use basic disengagement, advanced disengagement, and another type called cycle-based disengagement to perform all this decompose one step. Okay. Yeah, I'm sorry. I'm hoping not taking too much of the time, as it should start earlier, much earlier. But that's going to be that is all I'm going to talk about today. For some future directions, it will be great to improve further this n to the little one to polylog. That is probably the dream, but currently there are many barriers preventing our algorithm from it. There are at least 3. So our n to the little one is 2 to the log n to the 7/8. So 7/8 shows basically there are 3 steps, and each of steps takes n to the little one. And what about the same thing for crossing number with rotation system? Actually, we have shown they are sort of equivalent in terms of approximation up to polylog factors. So solving one problem gives you a solution of the other. And then at the very end, I want to make some small advertisement. Okay, so we are hosting a workshop on graph algorithms at DMX this summer, the week before Stock. So it will be June 12 to 15 at Rutgers University, and the goal is to like introduce the graph algorithms that achieves many good results in the recent 5 to 10 years to let's say PhD or senior undergraduate students or also postdocs. Okay, so I found that most like graphs algorithms that achieve success these years are hard and sometimes hard to master And we have sort of invited a list of brilliant speakers that are experts on these topics to give tutorials in the first 2 days. And so it will be a 4-day workshop. And the 3rd day and 4th day, we will invite speakers to talk about the most fascinating results in these past 5 years. So yeah, just want to make an advertisement here and hope some of you can be interested and join us in summer. So you can access through it to my website already. There's a link of this homepage. We haven't actively actively announced it, actively advertised it yet, but it will be soon, sort of in a week or 2. Okay, that's all I'm going to talk about. Thank you. Yes. Yeah, so that is, I mean, compared with our work, it's, I mean, written shortly, significantly shortly, a few, like 3 to 4 pages. It's based on planar separator theorem. If you, so it's by recursively cutting the graph along approximately mean balance cut and add the edges back. They have some bounds on how many edges, how many crossings they will be eventually introducing when adding them back. It's a very nice algorithm. Yeah, it's short, a little bit harder than the crossing number theorem, but still it's in 2 or 3 pages. That's all I can say. So by the way, this is also in bounded degree graph. Actually, their result is given a graph, it can compute a drawing with summation of degree square plus CRG crossing. This is their result. When bounded degree, it's n plus CRG, a summation of degree square. This can be sort of replacing every vertex with a grid and then applying planar graph, planar separator theorem. So this is where degree square come into play, if it is making any sense. Okay.